Hi everyone. Today we're going to be talking about Le Chatelier's principle and how you can predict where an equilibrium reaction will shift based on a stress that we apply to an equilibrium system. So if I stress something out, which way is the balance going to shift? So Le Chatelier's principle states that if I apply a stress to a system in equilibrium, the system will shift in that direction, or in a direction, not necessarily that direction, but in a direction to relieve that stress. So you can think about it almost like a seesaw. If I have a seesaw that's nice and balanced, where equal weighted people are on either side, but suddenly I take one of those people away, or I add another person to one side, it's going to stress out that equilibrium and one side is going to shift. So what we see is this relief of that stress that we are trying to do, and what we'll see happening, that relief is going to cause a new equilibrium to be established. So it's going to shift itself over. So there's typically a few different types of stressors that you can do to a reaction. The first thing you can do is stress out the reaction by adding or taking away some chemicals. So I'm going to just make up a random equilibrium expression like this. I don't know, I just made it up, okay? So I have my reactants on the left, my product on the right, and if I increase something's concentration, the system will shift away to use it up. So let's say I were to increase A, meaning I put more of A inside of the reaction. That means it's going to try to shift away from making more A to make some product. So it's going to shift to the right, shifting away from the thing that I'm increasing. If, however, it's the opposite and I'm decreasing, so let's say I'm decreasing the amount of A2B2, so I'm reducing how much is in that equilibrium. What happens then is I want to make more of it. I want to rebalance things out, and I'm going to shift towards the thing that is being reduced. So the big thing here to remember, concentration increases, shift away. Concentration decreases, shift towards. We want to make sure that we are balancing out any of those changes that occur. The other thing that we can do with an equilibrium expression is we can mess with its temperature, so we can make things hot or cold. So I'm going to use that same example I had before. A plus B makes A2 B2, but I'm also going to add this extra word, heat. So in chemical reactions, if we see that there is heat on the left side, that means we have an exothermic reaction, okay? That means that we are losing heat as a byproduct of this reaction. If I were to look at the delta H for this value, it would be negative, okay? So if the heat is on the right, that means it's exothermic, and if the heat were instead on the other side, like I have to put heat into this to make this reaction work, then it would be endothermic, okay? And that means it goes before the arrow, positive delta H. So you have to figure out, is it going to be on the left or on the right? And for this example, I'm just going to put it on the right, okay? So this is exothermic. So if I were to increase the temperature of this system, so if I were to make this hotter, it will shift away from the side where the heat is. I don't want to keep making more heat if I'm increasing the temperature, so we would shift away from the side where the heat is. If, however, I decrease the temperature, then, because it's getting colder, I want to make more heat to re-equilibrate it, and I'm going to shift towards the side with heat, okay? So also keep in mind this information. So make sure that you know those endothermic and exothermic differences. The next thing we can see are changes in volume. So when we're looking at volume, remember that as volume goes down, pressure goes up, and as volume goes up, pressure goes down. So keep that in mind. When we have increased pressure, that's a stress to the system. So if we're looking at changes in volume, if I decrease the volume, pressure is going to increase. If I increase the pressure, it's going to be too pressurized, and I've got to try to reduce that pressure somehow. The way that an equilibrium will do that is to try to make less moles of gas. So increase volume, decrease the moles of gas. Well, I don't want to say decrease. I don't want to say it's decreasing, but it'll move to make less moles of gas. Okay, so we want to make less moles of that gas. And if we increase the volume, that's going to decrease the pressure. That means we're going to want to make more moles of gas because we want to either alleviate the pressure or restore it. So in any of these cases, I want to try to fix what that volume change is going to be. Move to make more moles of gas. Okay, so up to now, we've talked about changes in concentration, changes in volume, and changes in temperature. So let's look at some volume examples here. So we know that if I increase or decrease the volume, I'm going to be shifting towards sides with more or less moles of gas. So before I even look at these problems, I'm going to tally up how many moles of gas I have. And I'll know that something's a gas because it'll have that parenthesis G behind it. So in our first example, this has 4 moles of gas on the left. On the right side, 2 moles of gas. So if I want to decrease the volume, decreasing volume means increasing pressure. If I'm increasing the pressure, I want to make less moles. So that means we're going to shift towards the right in this example. Okay, we would shift right if we're decreasing the volume. If we're looking at the next one, this one's a little bit tricky because you might look at this and say, oh, there's 7 moles here, but that's not true. There are not 7 moles of gas. There's 3 moles of iron metal, that's a solid, don't include it. This side only has 4 moles of gas, so it's only the gases that we care about. So on the right side, I don't really care about this iron oxide, I only care about the hydrogen. So in this example, it says increasing volume will cause a shift in which direction? Because there are equal numbers of moles of gas on either side, no shift. Nothing can happen because there's no mole difference. So there's no way to alleviate or restore the pressure. It's just going to stay as it is. The other thing that would potentially cause a change in a reaction would be a catalyst, but in this case, it causes no shift in an equilibrium. A catalyst only reduces the activation energy in a potential energy diagram. So if you think like this is a chemical reaction that has to occur, energy is on this axis, we have to go up in energy and then eventually hit this cresting point, and that's where the reaction is going to proceed forward. The amount of energy that takes from the reactants all the way up here is going to be what's called the activation energy, okay? The catalyst will reduce how much energy you need. So I might only need to go up this much so I can save some energy. So it's not going to necessarily like cause the reaction to change in terms of its equilibrium. It just gets it there faster, so it doesn't take quite as long. So looking at this application of Le Chatelier's principle, this is a reaction that happens inside of your mouth all the time. So as your body feeds on sugar and the bacteria in your mouth feed on sugar, they produce acid. That acid then reacts with hydroxide to make water. So if this reduces the concentration of hydroxide, it's going to shift towards the right. So your body is constantly trying to digest that sugar, and the equilibrium inside of your mouth is constantly changing. Some quick practice problems that we're going to do, just to give you an idea. I'm going to do this first one, and then the other ones I want you to try on your own and then check with me. Or, I mean, we can do more of them together. It's not a huge deal. But for this first one, which would cause this endothermic reaction to shift right? So you look through your options and you narrow down which ones wouldn't shift right. So if this is endothermic, that means I have to put the heat before our arrow. So I'm going to add that in. It kind of looks dumb. But I want to put it on the left side. Okay, so the heat is over on the left. And I want to try to see which of these shifts is going to cause a right shift towards the equilibrium. So if I decrease the concentration of dihydrogen monosulfide, we're going to shift to try to make more of it. That's left, and that is not one of the options that we could do. Okay, so it doesn't shift right, and discount it. Not going to work. If we increase the pressure, well, think about it. Increasing the pressure means we're decreasing the volume. If we're decreasing the volume, we want to go to the side with less moles, and that's going to be the left again. That one's out. Can't do that. If I increase the temperature, if I bump up the temperature, that means it's going to move away from the side with the heat that's towards the right, that one will be the one that allows for that right facing shift. D and E are both going to be incorrect as well. If I increase the concentration of carbon disulfide, I'm going to shift left to try to make less of it. So that's not going to work. Can't do that one either. And then the last one, decrease the concentration of methane. Okay, well, if I drop this concentration, it's going to shift left to make more of it. So again, not a left or not a right shift. So I'm going to cross that one out too. So the only one that it could be is C. We'll try another couple examples here, and then I will try to touch base with you if you missed class to see if these make sense. So let's say we're looking at this reaction. Which way is it going to shift if we add some sulfur dioxide? Well, if I add sulfur dioxide, I'm going to shift to make less of it. That's going to be to the left. If I look at my next one, I've got sulfur trioxide is removed. So I'm dropping this concentration. I'm going to shift to make more of it. So it's going to shift left again. And then finally, oxygen is added to the system. So we're increasing the amount of oxygen. We're going to shift away from making more oxygen. It's going to shift left. So if you're looking at these and you're like, wow, how am I supposed to remember all of these shifts? You can either like think about them logically and think what a system would do to try to fix itself when it's been stressed, or if it were me, I would just memorize them, to be honest. Okay, we're going to do this last one together, and then I'm going to let you try some on your own. So in this case, what would happen to the position of equilibria if you made some changes? We know that our delta H is negative. If you look on the front side of our notes a couple slides ago, we saw that a negative delta H means that this is exothermic. And if this is exothermic, heat goes on the right side, okay? So I want to keep that in mind. So if I add Hg3O, we're going to shift away from that, so we're going to shift right in that case. If I change the volume, so I decrease the volume. When I decrease the volume, I'm increasing the pressure. I want to move to the side with less moles of gas. So decrease volume, decrease moles of gas. This side has 2 moles, the other side has 7 moles. I'm going to shift left. And then this last one, if temperature is increased. If we increase the temperature, we want to move away from the side where the heat is, and that's going to be to the left. So if you have any questions with Le Chatelier's principle, practice kind of makes permanent with this. So I would just keep practicing, keep trying them out, and if you have any questions, please let me know.